In this video lesson, we're going to talk about video standards. This ties in with our body of evidence state standards, standard for systems, benchmark 1, which states students evaluate the quality and performance of a variety of systems. And so essentially we're going to be taking a look at the difference between high definition video and standard definition video. A video standard essentially defines the resolution, aspect ratio, frame rate, and codec for a specific type of video. So before we jump right into talking about video standards specifically, it helps to have an idea of how a camera or a digital video camera actually captures an image. So we're going to take a look at this short video called Deconstructed about how a digital camera actually works.
Deconstructed. You keep yours. We'll break ours. It's all about light. The digital camera. It's revolutionized photography by transforming light into electricity. Everything is there to draw in light, from the camera's buttons, controls, and dials down to the lenses. What the digital camera does with light is what makes it so revolutionary. It turns light into electrical charges that become the image captured on the screen. So how does that work? Let's break it down and zoom in on the parts that make it all happen. Every single piece of the camera is there to help capture the best image. But first, there needs to be light. To take a photograph, the #1 requirement is a light source. Light particles, or photons, leave the source, bounce off the subject, and enter the camera through a series of lenses. The photons then follow a designated path on their way from photon to photo. A series of lenses allows the photographer to capture the clearest image possible. This lens diaphragm is what controls the amount of light that the photographer allows in through the camera's opening, or aperture. After crossing the diaphragm, the lenses, and entering the aperture, the light bounces off a mirror and heads for the viewfinder. Before it gets there, the light is flipped over as it passes through a prism. That's so the image seen in the viewfinder is right side up. If the photographer likes the image, time to press the shutter button. The mirror lifts and the light rushes in. For a fraction of a second, the light is not heading in the direction of the viewfinder, but for the very heart of the digital camera, the image sensor. The duration of this fraction of a second depends on the shutter. That opens just long enough to expose the sensor to light. The exposure can be as short as 1/4000th of a second. That means in the blink of an eye, the shutter can open and close an incredible 1400 times. How? It takes 2 curtains. When the first one opens, the second one closes. So only a tiny amount of light squeezes through. Now, to the real heart of this digital revolution, the element that captures the image sensor. A tightly structured grid made up of extremely tiny light sensors. So tiny, each one measures just 6 microns wide. That's 6 millionths of a meter. That's less than 20 millionths of a foot. More than 5,000 of them could fit on the tip of a sharp pencil. But first the light must pass through something called a Bayer filter. That separates it into 3 colors: green, red, and blue. Because each light sensor can process only a single color, when the photons hit the light sensor, they are absorbed by the semiconductor material it's made of. For each photon absorbed, the light sensor emits an electric particle called an electron. The photon's energy transfers to the electron. That's the electrical charge. The brighter the image, the stronger the electrical charge is. So each electrical charge has a different intensity. A circuit board then converts the different intensities into computer language. digital bits and bytes, or a series of ones and zeros. They represent millions of tiny colored dots that make up a photo. The pixels. The more pixels in a picture, the better the resolution. This camera has a resolution of 3,872 pixels by 2,592 pixels. That's about 10 million pixels, or 10 megapixels. That means 10 million microscopic light traps, working with all the other camera's components toward a single objective, turning light into electricity to make taking pictures a real snap.
So, like the video said, basically a camera is just a light-sensitive image sensor, right? Light enters into the camera lens, and there's essentially a silicon chip in here that processes all of the photons and turns them into digital information, right? And it's turning all of the light into what are called pixels. And pixels are literally just a single point of light that are composed of these three colors, red, green, and blue. And when you combine them, it turns into this particular pixel, it turns into a purple color, right? Pixels color information is indicated on a scale of 0 to 255 for each of those colors. Right, so you can basically 0 indicates no color or blackness, right? Or sorry, no light or blackness, and 255 indicates full, like as bright as you can get for green, right? So we've got full color green, we've got about half brightness red and a third brightness blue, and that all combines to create purple. What happens if we had 255, 255, 255. So as bright as you could get on all colors. White, exactly, right? So this isn't like paint where you mix stuff up and you end up with like black or brown or something. Light, you have to think about it. It's like the brighter you get, the more towards white essentially you're getting. So yes, exactly. When you combine 100% of each of those color spaces, you end up with white. And so a single pixel is recorded on their image sensors, and basically all that a frame of video is a grid of those pixels. And the pixels are small enough, and they all just have different colors that when combined, they look like a full frame of video, right? They look like a picture. If you were to come up and look at the screen up here, there's actually like little squares on all of the there's like little squares on all of here, which are all just like individual pixels, okay? And the number of pixels that you get in a video frame is called video resolution. And video resolution is usually indicated by the number of pixels across by the number of pixels high. So right up here I've got a little example of a QVGA video resolution of 320 pixels by 240 pixels, or you'd call it 320 by 240. And this little 320 by 240, that's usually like a little web video, or kind of older style web video based on like a dial-up connection speed. Because essentially, video has to process information for all the little pixels in that screen. And back in the day, right, you couldn't actually get much information across internet lines. And so this was about the extent of the pixel information that could be transmitted. Stepping up in the resolution scale, we've got VGA video, so 640 by 480. And that's essentially like what these television, cathode ray tube televisions display in. They have a resolution of 640 pixels across by 480 pixels high. So you're kind of older style TVs. And then stepping up from there, we have 720 by 480, which is DV NTSC. And that's basically information that's recorded onto mini DV tapes, and in our class, this camera right here is a standard definition video camera. And strangely enough, anything shot DV NTSC ends up being displayed on these kind of VGA monitors, right? You end up actually losing a little bit of information from each side, right? So you actually get a little bit of stuff cut off kind of all around. And so you have to be a little bit careful when you're shooting using one of these cameras, so you don't get important stuff like right on the very edges. It's a little bit less important now because our output tends to be online or on the computer, and we don't lose that information. It'll just display as a full 720 by 480. Moving up from that, we've got what you'll see in iMovie. iMovie calls it the large format, and it's got a resolution of 960 by 540. Okay, and as you see, this is basically what iMovie is going to scale down HD video to. So it scales it down a little bit closer to standard definition, but it also, if you were to import standard definition video, it's going to upscale it a little bit and try to add some pixel information, which it works okay. It does an okay job doing, but it tries to make it a little bit larger. And then moving up from there, we actually get into what's considered HD resolution, like full HD resolution. So the first kind of HD resolution is 1280 by 720, or you might have seen this indicated as 720p. Anyone been shopping at like Best Buy or Target or something, looked at TVs? A lot of times you see TVs that are either 720p or 1080i.
Wait, what's the one? 960 by what?
960 by 540 is what you'll see in iMovie. It's called large.
So what's it, 720 by?
And then 1280 by 720, this is just like one type of HD resolution. It's what you'll see a lot of TVs, right? A lot of high-def TVs actually have a 720p resolution, meaning they can display